Well, thank you very much. It's been almost exactly 3 years since I was at LGLL. I came here in December 2019, and it's great to be back in person. So this talk is joint work with Martin Avasang, who is in the audience, Jeff Galkowski, who I saw lurking on Zoom. So hi Jeff, and of course myself, Euan Spence. Right, so this talk is all about the Helmholtz equation. I'm pretty sure I would be willing to bet that everyone in the audience has seen the Helmholtz equation before, not least because we had some talks earlier today in the FEM days about it. But just to make sure we're all on the same page, I've started off here on the left with the wave equation for a function, capital U, a function of x and t, space and time. And if we assume that capital U depends on time via this e to the minus I omega t, then this lowercase u function satisfies the Helmholtz equation here. And in a more sophisticated way, we could take the Fourier transform in time of the wave equation and end up at the Helmholtz equation. And this parameter k here that I put in red, this is the wave number. So this is equal to the omega. This is the angular frequency, so the frequency of the waves in the time domain divided by this wave speed c, which I'm assuming is constant. So k is the wave number, it's proportional to the frequency. Sometimes I will slip up and I will say that k is the frequency. And in particular, we're interested in this talk in the case when k is large, and this is known as the high frequency limit. So if you are just coming to the Helmholtz equation for the first time, I invite you to consider the two different limits. The first limit as k tends to 0, and the second limit k tends to infinity. And with the Helmholtz equation in this form, you see that if you just formally set k equals 0, we get Laplace's equation. And then down here on the bottom left, I've multiplied the Helmholtz equation by k to the minus 2. And here you see that if we now send k to infinity, then in that limit, the coefficient of the highest order term in the PDE is vanishing. So again, if you haven't seen the Helmholtz equation before, you can somehow guess that the limit k tends to infinity is going to be a harder limit to study than the limit k tends to 0. So here for concreteness, I've written down a kind of concrete Helmholtz problem that we're going to be interested in. So I have some impenetrable obstacle here called omega minus, and I have some data f, compactly supported data, let's say an L2, and our task is to find a u satisfying the Helmholtz equation in omega plus, that's the complement, the exterior domain of this obstacle. I'm assuming there's a 0 Dirichlet boundary condition on the obstacle, so this in acoustic waves, this is a sound soft boundary condition, and then I have this radiation condition. So mathematically, this is making sure the problem is well posed, but physically the interpretation is that these waves are going outwards to infinity. So they're generated by the source. They might interact with the obstacle, but they're all going outwards towards infinity. There's no waves coming in from infinity. And my goal, I've put in purple here, is to compute the solution of star. Right? So star is this problem. And why I want to compute the solution is only in the simplest possible case that this obstacle is a ball, can I somehow write down the solution explicitly. So in general, I want to compute an approximation to the solution. And I want to have arbitrary accuracy at arbitrarily high k, arbitrarily high frequency. And there's a subtle point here that you might say, well, Euan, you're interested in the Helmholtz equation for high frequency. Why don't you just compute the high frequency asymptotics, right? Find the equations that the k tends to infinity asymptotics the solution satisfy and compute these. And you can do this, but these asymptotics are valid in the limit as k tends to infinity. And it's very hard to get out of them a sort of, for a fixed k, arbitrary accuracy, right? If your engineer comes to you and says, right, our k is 100, I want 10% accuracy, it's hard to get that with these k tends to infinity asymptotics. So we're going to be going for the solution itself, but we're going to be using the tools and techniques that mathematicians have developed for studying this k tends to infinity limit, for studying these high frequency asymptotics. We're going to be using those in our task of computing the solution directly. Right, and so I should say a few things. So here this is perhaps a more familiar form of the Helmholtz equation for many people in the audience, but here I'm going to write it in this form because here every derivative is weighted with an inverse power of k. Okay, so I've got Laplacian here, there's two derivatives, there's a k to the minus 2. In the radiation condition, I've got a radial derivative, I'm weighting it by k to the minus 1, and it turns out that if you're trying to keep track of this k dependence for this high, as k tends to infinity, it's really convenient to have every derivative scaled with a power of k inverse. So the second thing to note is that I've called this a model Helmholtz problem. So our results are valid, not just for sort of Dirichlet boundary conditions, but the Neumann boundary conditions for at least smooth variable coefficients in the PDE. But we're sticking to this situation here for concreteness. And finally, I mentioned that I'm going to be using the techniques from PDE theory designed to study these high frequency problems. So these techniques are most comfortable when everything is smooth. So when we have a smooth obstacle, and if I have variable coefficients when the coefficients are smooth. However, these techniques are not limited to these cases, and so under sort of more non-trivial technicalities, I could reduce these smoothness requirements. And as a general comment, those of you who know me will know my general theme of my research is somehow using these techniques from PDE theory. It's the area of semi-classical analysis, where semi-classical essentially means high frequency, using these techniques developed by mathematicians to study these problems at the level of PDEs, using these techniques in the numerical analysis of these PDEs. Right, and so I wanted to, as soon as possible, put in front of you some pictures. So these are some motivating numerical experiments. And I should say that, so we actually, let's go back to the title. I talked about Helmholtz, and I talked about trapping problems, right? So we've got to pause here before the experiments, and you need to talk about trapping. So how do you tell if an obstacle is trapping or not? Well, you draw a big ball around the obstacle, and inside that ball, you consider all rays starting from every single point. And then you continue these rays. So here the problem is constant coefficients. The rays go in straight lines. And when they hit the obstacle, you can continue them according to this angle of instances, angle of reflection law that we learned in school physics lessons. And if all these rays, so you consider all possible rays, if all these rays leave this big ball in some uniform time, then the obstacle is non-trapping. But if not, then the obstacle is trapping. And so here, this particular obstacle I've drawn is trapping because you have a ray here that bounces around, gets stuck inside this cavity. And I guess, at least from my perspective, as a numerical analyst studying these Helmholtz problems, sort of up till recently, I viewed trapping as a sort of problem, right? This was a sort of an annoyance that you have trapping. It makes proving theorems harder. But of course, in applications, trapping is often the thing you want to exploit. So we had the talk earlier about the loudspeakers using trapping to create the bass, and these resonant spaces. So you have so trapping is often the feature of the Helmholtz equation, of these wave equations that you want to exploit indefinitely. And so that's a reason why we should look at these trapping problems more carefully, I think. Right, so here, okay, we got to the numerical experiments, and so here my obstacle is now these two kind of not quite rectangles, but smooth rectangles. And you see, so here, this is a trapping obstacle because there are trapped rays that bounce around between these two, these two curved rectangles. And I'm going to choose a particular, I'm going to show you sequences of experiments at these wave number k's, and they're going to be k's such that trapped waves can exist between these two mirrors. I call them. That's what we call these two mirrors. So what you need is the distance between the mirrors to be some multiple of half a wavelength, right? You want to fit some waves in here. So we're zooming. We're focusing on those particular. I'm going to say frequencies. I should say wave numbers k. And I've got this beam source. So this is my data. It's going to create some Helmholtz solution, kind of going in this direction. And I'm using, okay, I'm in free FEM days, I'm going to use the finite element method, and I'm using what's called the H version. So I'm going to talk about this a bit later, but in the finite element method, I'm approximating my solutions as piecewise polynomials on some mesh. I have two parameters, the mesh width H and the polynomial degree P. I'm going to keep P fixed, and I'm going to increase accuracy by decreasing H. And here this means I'm doing a sequence of computations as K increases. And so H is then going to decrease as some function of K that we'll talk about a bit later. So that's this sort of K-dependent H. But I want to highlight here that I'm going to choose a uniform H. So H is the same in all the computational domain. And so for these trapping problems, there's definitely a question about how do you actually compute an accurate solution. Here we're using as a reference solution, we're going to call it U tilde, and this is computed on the same mesh using degree 4, P is 4. And of course, we're doing the computations with free FEM. In fact, Mark in the audience is he did all the computations using free FEM, so he gets a tick and a smiley face. Right. So here so here so KR, because again this is the non-dimensional quantity. I'm writing approximately equal to 40. So this is K is chosen to be the sort of the near resonant value of K that's closest to 40, right? we didn't write down the exact k because it would have lots of decimal places, but so ki is around 40. Here we have our reference solution. So we've specifically, so there's a sort of beam coming in here and it gets some activation of the trapping, but we've specifically chosen our beam so that the sort of full trapping is not activated, right? I could have stuck the beam inside this, inside the two mirrors pointing this way, and I would have got some solution really concentrating on a trap ray, but we've deliberately done that. But nevertheless, here is a plot of the finite element error, and you see it's then concentrating. It looks like a trap mode between the two mirrors. And so if I increase k is 80, again, here's the solution. You sort of get some activation of the trapping, but the FEM error is again concentrated inside the trapping. Let's go a bit higher. Again, k r is around 120. Again, so the key point to take away from this experiment is that even if the solution itself is not kind of concentrated inside the trapping, the FEM error is. So here, there's a different domain. So this is a sort of horseshoe-shaped cavity where the trapping is stronger, okay? Because there are these trap rays that are more stable than just between these two parallel mirrors. And so here you have the beam coming in. It's not really even hitting the cavity, but still you get some activation of the trapping. And again, on the right here, you have a FEM error concentrated inside the cavity. And again, we're going to increase k here. And the story is somehow, so here now the solution gets more concentrated inside the cavity. But importantly, the FEM error is almost completely inside the cavity, at least on this scale, right? It's really, it looks like there's nothing out here. Everything is inside the cavity. And so the motivating question that sort of started Martin, Jeff, and I on this line of research was, well, can we establish rigorously what we're seeing in the pictures, which is if I choose a uniform H, chosen in the sensible way to maintain accuracy as the frequency increases, can one prove that the FEM error is smaller away from the trapping? And in fact, I've given some talks earlier in the year with that being the title. And one of the motivations for this is, again, as we heard this morning, if you want to compute the far field pattern of the Helmholtz solution, you only need to know the solution in some annulus around the scatterer, right? So if I knew the solution in some annulus around the scatterer here, I can compute the far field pattern. And in some applications, the far field pattern is exactly what you want. But you see, so in this situation here, our far field pattern has been much more accurate than the solution inside the cavity here. So again, that was our sort of motivation for thinking about the error in subsets of the domain away from the trapping. So that was the sort of story we started on, this first question, and then we sort of got onto the question, which is actually, well, can you choose a non-uniform H? Again, it has to depend on K, to sort of, and then it sort of opens up the question about, well, what goals do you want to achieve, right? So maybe you want to actually control the error inside the trapping, right? So then the question is, what's the minimum requirements on this non-uniform H to achieve that? But let's say you want to control the error away from the trapping. You don't care about making an error in that trapping region. What, again, are the sort of minimal requirements on H to achieve that? And so in this talk, I'm going to present to you results that are going to sort of answer both these questions, 1 and 2. But right, so we've got some finite element people in the audience, and I'm sure you're all thinking, well, Euan, you've got these cavities, you've got the error concentrating inside the cavity. You just need to refine H a lot inside the cavity, right? Take H to be really small inside the cavity. And that is, of course, necessary. But I'm going to try and just convince you now, scare you now, that might not be sufficient. With non-uniform meshes, a cautionary tale. And so this is in a paper that Martin and Jeff and I wrote earlier this year. And what I'm doing is, so these are plots. So what am I doing? I'm solving the Helmholtz equation in a rectangle. And my exact solution is some wave propagating to the right. So just a simple constant coefficient Helmholtz problem, impedance data, exact solution propagating to the right. And here is the error on where I have a uniform mesh. Of course, H is H1. And all these errors are plotted on the same scale. And then here is the error when I take a uniform mesh with a mesh width H2, which is much smaller than H1. And you see, so here, this kind of blue is then smaller further down the scale than this kind of purple up here. So this is sort of corresponding to what you expect. You decrease H, you get more accurate solution. here now, for this picture that's occupying center stage in the slide, we've got a non-uniform mesh, where on the left, the mesh width is H1, and on the right, it's this smaller mesh width, H2. And you see here that actually, you might expect then the picture at the bottom to just be, well, this half here, because H is H1, and this half here, where H is H2. But actually, the error when H on this right-hand side is much bigger than it was just for a uniform mesh of size H2. And so what's happening here is that I have error on the left, and it's propagating to the left. In fact, you can even see, propagating to the right, propagating from the left to the right. You can even see that this error on the right is this sort of low frequency wave here. So the key point here is that errors for these wave problems are propagating from some parts of the domain to other parts of the domain. And so, we can make H2 as small as you want here, and it's not going to decrease the error on the right of this plot. And then just to sort of further emphasize this point, here is exactly the same experiment, but now the exact solution is a way of propagating upwards in the domain, right? So even though the solution is propagating upwards, the error here, there's still error propagating hit from the left to the right. So one of the sort of key points I want to emphasize, key takeaways from this talk, is that using these non-uniform meshes, you need to be careful about the propagation of the error, and that's something that we're going to need to control if our goal is to design such non-uniform meshes. Right, so here I've got again the title slide, and that was the sort of trailer to get you all excited about the talk. And so now I want to sort of get into a bit more of the details. And so I put this title slide up here again just to emphasize, okay, here I have this model Helmholtz problem, this exterior Dirichlet problem that we're gonna be studying. And here again is the goal: compute the solution to arbitrary accuracy for arbitrarily large k, in particular for these trapping problems. Right, and so this next slide is sort of everything you need to know about the k dependence of the Helmholtz solution operator, right? So this is a PDE theory slide, and of course, our goal is to approximate somehow the Helmholtz solution operator. So how this object depends on k at the continuous level is actually going to be relevant for our approximation of that operator. And so I want to measure the data to solution map. And look at it, I've made a disaster. I had my data here was F, but my data here was G. So I'm going to try and fix this. Look at it live with this is an advantage of doing it live here. There we go. Okay, so I wasn't a very good F. Here we go. Right, so I want to look at the data to solution map, F to U. And so I'm looking at the Helmholtz equation. This is a second order linear elliptic PD. The natural space to measure the solution is H1. But here I have a sort of technical issue that the Helmholtz solution is not in H1 of this whole exterior domain because of the radiation condition. So instead, we're going to measure the H1 norm of U on a ball of radius r. And again, r is just some arbitrary. It can be sort of it can be arbitrarily large. So we're not losing any information here. And so I'm working on some ball of radius r that contains the obstacle, and I'm looking at the data to solution map F to U, and I'm looking at the norm of that map. And so I'm following my earlier rule that so here I've got the H1 norm on the right. So it's the L2 norm of the solution, the L2 norm of the gradient. But I'm weighting each derivative with a power of k inverse. And the advantage is that if I'm doing that, then the norm of the data solution map for the Helmholtz solution is the same in whatever spaces this map is defined, right? So here I've defined the norm from L2 to H1, but it could be from L2 to H2 or from H-1 to H1. In all those spaces, along I'm weighting derivatives with k. Somehow the k dependence is the same. And so we talked about what trapping and non-trapping were. These are the key geometric properties that are dictating the behavior of the norm, how the norm behaves on k. And if the obstacle is non-trapping, then this norm of the solution grows with k as k increases. So I've written here twiddles to mean somehow it's bounded above and below by some constant independent of k, time multiplied by k in this case. And then here I've drawn three different types of trapping domains where the trapping is weak here and strong here. And the overall picture I want to say is that the solution operator then grows faster with k, and the stronger the trapping, the then faster growth. And so this is reflecting the fact that when I have a trapping problem, the ill conditioning with respect to k gets worse. So here, the weakest form of trapping is when I have these two balls. I have a weakly trapped ray here. There, the solution operator goes like k log k, and again, this is sharp through some sequence of k's. So that the trap wave can exist there. Here I have these two rectangles. Here the solution operator grows like k squared, and then here I have this. So if the boundary of the obstacle contains part of an ellipse, then this solution operator grows exponentially through a sequence of k's. So this is really bad. Although in general, the solution operator is polynomially bounded in k for most k in a which way you can make mathematically precise this notion of most. So what I want you to take away from this slide, what's important for the future, is that non-trapping problems, you get growth like k. Trapping problems, it can grow much worse than k. Most of the time you have some polynomial bound, and in fact the theorem I give you at the end is going to be valid under this under this polynomial bound on the norm of the solution. Right, so that's all you need to know about the Helmholtz solution operator. Now, right, so we want to solve this problem with the finite element method. And the first issue you need to address is that the domain, this exterior domain omega plus, is unbounded. So we need to somehow truncate this. This is a classic problem in applied maths. And I look at it. Look, normally when I'm talking, I wave my arms around, but now I'm doing this with the iPad. I cannot somehow wave this left hand because the iPad's going to sort of resize itself. So I'm going to confine my waving to my right hand only. Okay, so this question of how to truncate the domain, this is really sort of classic, and we're going to truncate with a PML, a perfectly matched layer. So what you do is you introduce some boundary, and then which I've drawn as a circle, but doesn't need to be, and then in some annulus around that boundary, you change the coefficients of your Helmholtz problem, and if you do this in a clever way, then the solution inside the boundary is very, very close to the restriction of your Helmholtz solution to that domain. And in fact, with a perfectly matched layer, the solution is exponentially close as you increase the width of the layer, as you increase these scaling parameters in the layer, and as you increase the frequency. So I haven't written down the details because if you don't know about perfectly matched layers, now is not the time to learn about it. But the message is we can truncate and control the error. And in fact, I've committed this notational crime in that I've denoted the solution of this PML problem as U itself, because you should really think of the PML solution as essentially this scattering solution itself. And there's a Dirichlet boundary condition on the outside of this PML, and that means that now somehow my problem is posed in the space H01. And here's my Helmholtz variational form, which again I just get by multiplying the Helmholtz PDE again with this sort of variable coefficients due to the PML, multiplied by a test function and integrated by parts. And then so that's the variational formulation. And then we apply the Galerkin method. So we're going to find some finite dimensional subspace. And so here in green at the bottom, this is just following the instructions of green in the top, but I've replaced the space H01 with some finite dimensional subspace. And again, I'm using these classic finite element subspaces consisting of piecewise polynomials. I'm going to consider fixed degree P, and the mesh width H is going to be then varying and decreasing to obtain accuracy. Okay, so I'm hoping this is familiar to at least all the attendees of FEM days. And then you have this classic question then, a natural question: how quickly must H decrease as K tends to infinity to maintain accuracy? So that's the question we're going to talk about for the next few minutes of this talk. But as a warm-up, we're going to first have the question: well, how small must H be to accurately approximate a Helmholtz solution? Let's not worry about computing the solution with a FEM. Let's just say we have a Helmholtz solution, and I want to approximate by piecewise polynomials. Well, how small do I need to make H as a function of K? And so here I've drawn some oscillatory solutions, and here with a dashed line is a piecewise linear approximation to that solution. And so here at the top I've taken five points per wavelength, and it's piecewise linear, so P is 1, and you can still sort of see these dashes, but here at the bottom I've taken a sort of classic 10 points per wavelength, and depending on how good your eyesight is, you can just see a little bit where it's not where you can see a little bit where the approximation is by the eyeball norm different from our oscillatory solution. And this is because, so what's underlying this is the wavelength of the oscillations is 2 pi over k, and so these functions are close to linear, in particular well approximated by polynomials, once h, the mesh width, is sort of much smaller or on the scale of k inverse. So to make this more precise, there's this classic, so again, FEM people will know this classic approximation result, which says, I measure the smallest possible error in approximating a function u by a piecewise polynomial, and I'm measuring this in the h1 norm. And if I have degree p polynomials, and if my solution is an hp plus 1, then I get an h to the p times the hp plus 1 norm of u. But all I've done here is then converted that result to work in these weighted norms k, right? So here this is the h1 norm weighted by k, and here this is then the hp plus 1 norm where each derivative is weighted with a k inverse. So I'm hoping that people in the audience who are familiar with this classic polynomial approximation theory result can just sort of believe or do on a little bit piece of paper, check that then this is the result when you work with these weighted norms. And so you see then I get this quantity hk to the p, and so if hk is bounded, or in this case less than 1, then I'm getting sort of a uniform accuracy relative to the norm of u as k increases. So given this, you might think that, well, for my finite element method, I just need to take hk to be some sufficiently small constant, right? A sufficient number of points per wavelength. So that's the natural thing to think. But this is not the case. So hk is sufficiently small is not sufficient for accuracy of the h version of the finite element method as k tends to infinity. And this is this classic pollution effect. So in fact, last night when I was preparing this talk, I was trying to find out who first coined the term pollution effect. And so before 1995, it hadn't been used in this Helmholtz context. And then in 1995, there were 3 papers by the combination of authors, Buschke, Eilenberg, and Zalter. So different combinations. These authors all wrote some papers in 1995 calling this effect the pollution effect. So what's happening here is I'm going to plot. So it's the ratio of the FEM error, so u minus uh, that's the FEM solution, divided by then the smallest possible error I could hope in approximating u with elements of my finite dimensional space. And so here on the left, this blue curve is when hk is constant, and this error is then increasing with k. And again, on the right here, this blue curve is when hk is constant, and this curve is then increasing with k. And then you start to play the game. Well, hk is not sufficiently small. Let's then try and find out what mesh threshold is. And I should have said these pictures are plotted for scattering by a ball. Okay, so I have just a 2D ball scattering of a plane wave by a ball. Right. So hk small is not hk sufficiently small is not sufficient for accuracy of the h version of the finite element method as the frequency increases. So what are the conditions that you need on h? And okay, so there's sort of two conditions, because there's 2 sort of natural ways to measure the error. Okay, I'm going to slow down because maybe this is one of the most technical slides in the talk. So the first way of measuring the error is to demand that the Galerkin error, the FEM error, u minus uh, is bounded by a constant independent of k times then this smallest possible error in approximating u in the space. Okay, and so if the FEM error were the smallest possible error, the method would be optimal, but somehow being bounded by a constant of times that error is then known as quasi-optimal. So one requirement could be that, so a natural requirement is to ask for this k-independent quasi-optimality. And then it turns out that you can prove and you can observe empirically that what you need hk to the p times rho of k, this norm of the solution operator, to be sufficiently small. Right? Remember, rho of k, even in the best possible case that the problem is non-trapping, is growing with k, and so that's telling you that hk sufficiently small is not not enough. Although it's also telling you that the larger p is, the closer you somehow get to hk sufficiently small being enough. And often I'm noting this is often called the sort of the asymptotic regime, where your solution is quasi-optimal. And some fans of the asymptotic regime in the corridor there. And another requirement is, you might say, well, I want actually to control the relative error of my solution, right? Again, again, once I search, in the engineering journals, how many people are actually looking at causal optimality, and it's very few, but how many people are looking at relative error, and it's lots. So you can ask for the relative error to be sufficiently small, and here you need a less stringent condition. You need that hk to the 2p times rho of k is sufficiently small, and I should say that, of course, and here you need also that the data is k oscillatory, right? You need your data to be some sort of physical data coming from a scattering problem. I mean, yeah, this is not an important. This is not a controversial requirement. And so actually, so I wanted to talk about in purple where both these bounds are coming from. And again, that's why I'm trying to be slow here, because this is perhaps a bit technical. And actually to keep that bound with us, I've written on the board here. I wrote on the board when I wasn't thinking I'd be standing in front of that area of the board, but perhaps later I'll stand back and reveal it. And so what the sort of bound underlying these results is it's again saying if hk to the 2p rho is sufficiently small, then I have sort of quasi-optimality with this constant being hk to the p rho. So of course then hk to the p rho being sufficiently small is enough for quasi-optimality. Okay, great, that's the result up here. But then what you do is you use your polynomial approximation theory, right? You use a polynomial approximation theory to get an extra hk to the p. And if your data is k oscillatory, then your solution u is k oscillatory, and this high norm of u is bounded by a low norm of u. And then that's where you get this condition that hk to the 2p rho sufficiently small is enough to bound the relative error. Okay, so I'm conscious that if you're seeing this for the first time, that's possibly a little bit technical, but I'm going to sort of write up so we're going to carry with us this bound here in purple forward, because we're going to prove some analog of that. Right, so I've just been stating these results without telling you where they come from, and so for in the interest of time, I won't go through this slide sort of bullet by bullet, but I just want to acknowledge that there's been vast amount of research in obtaining what I call these mesh thresholds, right? These conditions, about how H must depend on K, and also you can study this pollution effect by dispersion analysis that I completely ignored here, but want to acknowledge. And so here are some of the sort of key works on that. And one thing to say is that okay, for these sort of two different thresholds, the threshold for quasi-optimality and the threshold for the relative error, only very recently were these actually proved for sort of general Helmholtz problems. And so this quasi-optimality result was proved in a few years ago by Théophile Chaumont-Frelet and Serge Nicaise. And when I say general Helmholtz problems, I mean somehow you assume your statistical uniform is continuous, you assume it satisfies a Gaussian inequality, you assume you have electric regularity, and then you prove the result. And then just under a year ago, Jeff and I, under these assumptions, again proved this result about the relative error. So yeah, so just to acknowledge that it again took us, the numerical analysis community, a long time somehow from this initial work by Eilenberg and Babushka highlighting highlighting these thresholds. It's taken a long time to somehow prove them in the most general settings. Okay, so that was a sort of crash course on if you're choosing a uniform H, how small must it be as a function of A to get accuracy with these two different measures of accuracy, right? Quasi-optimality and the relative error controlled. And here we have then these two questions I started with in the trailer, but just slightly rephrased. So now it's for a uniform H satisfying either one of these conditions, right? For making the solution quasi-optimal or making the relative error controllably small, can one prove that the FEM error is smaller away from trapping? And then the second question, which is just phrased the same, can I choose a non-uniform H to achieve different goals? Right. So let's talk about these. So we're going to think about a non-uniform H. So we want to think about how to split up the parts of the domain, right? Like what are the important, what is the important criteria in order to decide which parts, how we should split the domain. And the criteria is all about the rays. So let's go down to this picture here at the bottom left. And here is my impenetrable obstacle. So again, I'm thinking about this constant coefficient Helmholtz problem. an impenetrable obstacle. So here I'm just shading in here. Here's the obstacle. And the first region I'm going to define is this cavity. I'm going to call it omega capital K. The capital K is because in semi-classical analysis, the trap set is called capital K. This is just some notation we solved from there. So inside the cavity is going to be some region that's a sort of purpley pink color. Then in green, I'm going to have again what I've called the visible set. Omega sub gamma. Again, the gamma is because of the semi-classical stuff. Don't worry about that. But here, so these are points. So I'm in the visible set if I'm not in the cavity, but if I can reach the cavity via some ray, which again for this Helmholtz problem is a straight line, right? So here I can reach. Here I can reach. And okay, so here we've been a bit conservative because I can't. Obviously, if I'm sitting here, I can't quite reach the cavity. But I've been overly cautious to make sure that all the rays that can sort of come in here at some very shallow angle are contained in this visible set. Then I've got in blue this invisible set, which is basically all the points which you can't get into the cavity via some straight line ray. And then I've got this set in orange, which I've called omega p, and this is a set contained inside the PML region. So for technical reasons, you can't make it exactly the PML region because the PML turns on, and you need to just be just inside the PML region. Okay, so this is the picture of the regions I want you to carry forward with you here, and in each region I'm going to use a different H, right? So in the cavity I'm going to have H being smaller than HK. In the visible set, H smaller than H gamma. In the invisible set, I'm going to have an HI in blue and an HP in the PML region. And here on the right then is for this two mirror example, I've plotted the regions, but then there's also a plot of the mesh. And it's a plot of the mesh where we're taking. So again, you can expect. So what's going to happen is I'm going to need to take the HK inside the cavity to be very small. So this mesh is very small, which is why on this scale it's just going to come out as completely black. Then in this visible set, I'm having a slightly bigger H. Here's the visible set. Then in the invisible set, I'm having a bigger still H. And then in the PML region, you can see I'm having an even bigger H. And so to get slightly technical, what we need is the mesh overall to be quasi-uniform on a scale of K inverse. So any ball that's a radius proportional to K inverse, I need the mesh to be quasi-uniform. So I'm transitioning between these regions, respecting that requirement. Okay, so we've got these four regions, and we've got different mesh thresholds in each region. And the structure of the main result. So what's it going to look like? It's going to say if these four mesh thresholds are all sufficiently small in different K-dependent ways, then the Galerkin solution exists, is unique, and I have this bound here. So it's going to be a vector of the errors in each of the regions is bounded by some matrix, then times the best approximation error restricted to each of these regions. Okay. And so I'm highlighting, so again, like before, and you've got up here on the board, before I had just a global H, I had HK to the 2p row of K sufficiently small, and here then I had just the global H1 error bounded by 1 plus HK to the row times then this best approximation error. So I'm looking for some analog of that, but where I've got these four different regions. Okay. So that's the sort of structure. I wanted to highlight the structure before we get into the technical stuff, or more technical stuff. So there's two ingredients in the main result. Let's start on the right because this is a bit easier. There's the mesh width matrix. Okay, so this is just a matrix where the diagonal entries are these four different mesh widths, and it's 0 elsewhere. Okay, and then we have what's called the communication matrix. And this is somehow now, so what is this? This is the norm of the solution operator where your data and where you measure the solution are restricted to different regions. So for example, if my data is in the trapping and I look at the solution in the trapping, then my solution, then my normal, my solution operator is rho. Okay, so we know that globally it's rho, so somehow there has to be a rho somewhere, right? And the worst possible behavior of the solution operator is data in the trapping. I look in the trapping, I get rho. But then I get improvements if one of these locations is not in the trapping. So if my data is in the trapping, but I look in this visible set, then I get square root of k times rho. And because so when the problem is trapping, rho is bigger than k, and so this is smaller than rho. And then when both my data, if my data is in the visible set and I look in the visible set, then I get k, right? So it's saying that if my data and where I look are away from the trapping, then this data to solution map just behaves like it were a non-trapping problem. Okay, so physically, oops, again, see there, I get excited. Physically, this sort of makes sense, but this is the mathematical realization of that. And I should say, so here I've written these zero entries are not strictly zero, they're super algebraically small in k, but this is a technicality. But you should just think of them as zero. And so of course, proving these results is there's again a long history, and it's difficult results, technical results to prove. So Nicola Burke and then Cardoso and Vodev proved this sort of block here, when you're away from the trapping, when your data is away from the trapping, you look away from the trapping, you just get k, and Dachev and Vashi then proved these results about when one of these locations is away from the trapping. And so this is where this semi-classical analysis, this PDE theory of the Helmholtz equation is coming in. It's informing our choice of these different regions, and it's telling us how this solution operator behaves in these different regions. Okay, so I have a mesh width matrix, and then this communication matrix. So this communication matrix is you should think is it's playing the analog of rho, right? Rho was the norm of the data solution map where everything was measured everywhere. Now I have this curly C, which is again data to solution, but it's being more careful about where you're measuring and where you're looking. Okay, and then the last ingredient for the result is I compose this matrix here. I have my mesh width matrix. I multiply by k. I take p, and I compose it with the communication matrix. And this is then the transition matrix of this graph that we've drawn up here, or that's been drawn in ticks in LaTeX up here. And so how you should think about this, and at the heart of the proof of the theorem, is it's about controlling how the errors propagate. So for example, let's say I'm in the trapping here, omega k. I make some error, it's hk to the 2p, and I make some error hk to the 2p, and then I want to look at about that error propagating back to the trapping. Well, the norm of the solution map from going from the trapping to the trapping is rho, so somehow that's the propagation of error omega k to itself. But I could go in the trapping to the invisible, to the visible set. So I make an error of h trapping k to the 2p, and then the norm going from the trapping to the visible set is the square root of k times rho. Okay, so that's just a consequence of how this transition matrix is defined. But you should think about it as in this is what's sort of quantifying this propagation of error that we saw in those pictures at the beginning, right? The error in different domains is propagating to the other domains, and it's propagating according to somehow this relationship. And so then there's some sort of graph theory that we need to do, because I define this matrix V. So I'm given some sort of constant. And it turns out, because what happens in the proofs is I want to invert. I have an equation satisfied by my error, but it's got this I minus C inverse T, and I want to invert this I minus, C star T with C just some constant. Okay, and so this is given by this sum of powers of this C star T. And if you remember, so if you have the adjacency matrix of a graph and take the powers of this then counts the number of paths of certain lengths between different nodes of the graph. And here we have the same thing, although we have a graph and the entries of the graph, we're calling them weights that correspond to different edges. And then so taking these powers of this matrix and summing them up, this is the same as summing over all paths from the ijth entry of this is the sum of all paths from node J to node I, and essentially the product of the weights along the paths. Okay, so again, controlling this is controlling then how the error propagates throughout this graph. Okay, so that's all the ingredients, and here we then have the result. And again, I want to emphasize it's the analog of what we had before. So before we had some condition just on some global uniform H. Well, now I have some condition on all the different H's, and you see, so my condition on the H for trapping, this is the same as this global condition we had before, right? It's H trapping K to the 2p with the norm of the solution operator rho. Well, that's what we had before, but on the H's that are elsewhere, I have less restrictive conditions, right? I've got rid of the rho and I've just put K's. Okay, and in fact, in the PML, I've just got HK. So that's a less restrictive condition than we had before. And before we had the error bounded by 1 plus rho, then times HK to the P. Here I have a matrix identity plus. Okay, so here's my analog of the HK to the P, and then the analog of this matrix of the solution operator rho. Well, now it's this communication matrix, but times this matrix involving the graph, which is dictating how all the errors are propagating around this graph. Okay, so that's the bound in all its glory or scariness. So let's now go back a little bit to our question, which was, can I sort of control? Can I choose different H's to get different goals, right? To control the error in the trapping or to control the error away from the trapping. And I'm going to summarize these in this table. It's going to have six rows. And 2 of these rows I've written down already. These are the conditions for uniform meshes that we have already, right? So as we know that if we take all the mesh sizes to be this global H, and I want K independent causal optimality, then I need this condition here, this HK to the P row sufficiently small. And if I want the relative error to be controlled, like I want with a uniform mesh, I have HK to the 2p times rho sufficiently small. Okay, so these are going to be special cases of our theorem. But I'm going to put additional cases in. And so the first case I'm going to put in is I'm going to still keep this goal of K independent causal optimality, but now I'm going to weaken. So in the trapping, I've got this, I've still got HK to the P times rho sufficiently small. But now in the other regions, I've got HK to the P times some quantities that are smaller than rho sufficiently small. Okay, so I can have coarser meshes in the regions that are away from trapping. And I've written, so there's this middle column here is the asymptotic cost. So you see the asymptotic, because in the trapping, I still have to respect the kind of nasty mesh threshold. The cost with respect to K is the same, but somehow I've got a smaller constant because now the constant depends only on the region, the area, the size of the trapping region, and not sort of everywhere. Okay. And now this is going to answer this first question we had, which was if I have a uniform mesh, is the error smaller away from the trapping? It's because in both these situations, I'm achieving K independent causal optimality. So what's the gain in using a uniform mesh? It's that the error is smaller away from the trapping. So I'm gonna, okay, so in the interest of time, I'm gonna skip the maths of that and just show you that graphically a bit later. And then so here I've then filled in the fourth row of this table we see, which is the exact analog. I've sort of taken this threshold up here for K independent causal optimality. I've replaced all the P's with 2P's, and I've got now some condition for the relative error being controlled. Because again, that's what we had with a uniform mesh. I take the condition for a uniform mesh, I replace the P's with 2P, and I get the condition for the relative error. So if I had longer, I would have got you all to guess what that condition for the relative error being controlled was. And again, so this has some smaller cost, some smaller asymptotic cost, and what's happening is that when I take a uniform mesh, I'm getting smaller error away from the trapping. That's what that's giving you. Okay, so now there are 2 more rows to fill in here, and these are going to be, so in fact, let's just go for a guess. Right, so who can guess what this sort of theoretical guarantee for both these boxes is going to be? stand off here. I'm going to pretend that I have all the time in the world. Okay, so here, this is the relative error control everywhere, right? And this is so where else might I want to control the relative error, right? I talked about. So let's again. Away from the trapping, yes. So this is going to be what we call K-independent quasi-optimality away from the trapping. So I need to be a little bit careful about what I mean there. I mean that I have my quasi-optimality bound, but this norm on the left is measured everywhere away from the trapping, right? So the H1 norm away from the trapping is measured by is bounded by the best approximation everywhere error everywhere. Okay, and again, so I have so I'm conscious. You see this table for the first time. There's all this, these colors and these conditions. But the point here is that I'm controlling the error away from trapping, and I'm weakening things, right? So here I have a row, but I'm replacing it by square root of k times rho. So going down these columns here, I'm weakening the conditions on my mesh, and similarly here, I either weaken the conditions on my mesh, and here I'm controlling the relative error away from the trapping. And so in fact, I should have said that the highest rows here, this is the finest mesh, the mesh with the largest cost, and this is the cautious mesh, the mesh with the cheapest cost. Right, so I'm going to have just three slides in the numerical experiments, and then we're going to be done. So this is three sets of numerical experiments. This is the data and the solution. So I'm going to call I've got what's called a beam inside, where I've stuck a beam here like I had before, but now I really want to kind of like activate the trapping. So I've got the beam inside going this way, and here's a representative solution here. You can see there's a large concentration inside the trapping, and I've got the beam outside. So here the beam is coming outside. I'm making sure that it kind of bounces inside the trapping, and here you have a representative solution here. But it's important to say that so for example, the K dependence of the solutions is then different, because this is activated. The beam inside is activating the trapping much more than the beam outside. Here I said, okay, so one of this first task we set out to explain was, is the error smaller away from trapping when you have a uniform mesh width, and our theory when you input all this stuff and turn the handle, what comes out is you expect the error in the visible region divided by the error in the trapping to go down like k to the minus half in this particular setting. And here are then some plots then for the beam inside, the beam outside. This dashed line is k to the minus half. I'm plotting exactly this ratio, and you see that both of them, as k increases, settle down to achieve this asymptotic rate. Okay, so that's our theory, and somehow seems to be achieved in this scenario. But I'm highlighting that here we've used information that sort of both solutions activate the trapping to a sufficient extent, right? So if I had a beam and it sort of came in from the left here, and then it just sort of bounced off and didn't see the trapping, then I wouldn't get any improvement. And so I'm saying that we've input that information into our theory. Okay, that was experiment number 1. 2 more experiments to go. The next one is this K. So here now, I've chosen the threshold to get K independent quasi-optimality, but it's sort of via this then non-uniform mesh. And here I'm plotting. So we're plotting the ratio of the errors in each domain, omega I, where I ranges in these different regions, divided by the global best approximation error. The theory predicts all are going to be bounded by a constant, and so it's in this picture. The main takeaway message is that yes, these things are bounded by constants. In fact, the errors in the visible set and the invisible set seem to be decreasing a bit, and we can actually again get into the details of looking at what the solution is, and then explain and in fact predict and see the K dependence of these decreases. And then the final experiment is choosing the coarsest possible mesh. So this was one where the relative error was controlled away from the trapping, but somehow that was this bottom row of our table. Here now the theory predicts that we have these bounds. So it's of the form H1 error bounded by the best approximation error, not with a constant independent of k, but with a constant that grows with k. So in the visible set, it grows like square root of k, and in the trapping, it grows like square root of rho. And for these two mirrors, rho is k squared. And here you see that we've got, in fact, a grow of square root of k for the visible set, and then growth of k for the trapping. So again, in this situation, the theory is somehow confirmed. Okay, so that's the end of the talk. But sort of two take-home messages practically for the FEM practitioners in the audience. So even for non-trapping problems, you only need to take a fixed number of points per wavelength strictly inside the PML region, right? I talked about how our theory was designed for the trapping, but even if you have a non-trapping problem, we prove this. So you can start right now. Don't respect the pollution effect inside the PML region. And there's be some microscopic savings everywhere around the world after this talk goes live. And then the second conclusion is that for these trapping problems, you only need to respect the existing mesh thresholds inside the trapping region omega k, and you can lose larger mesh widths, fewer degrees of freedom elsewhere. Okay, and so those mesh widths are going to be they're in the slides of these talks. They're going to be up on the LGL website. There'll be a preprint with all this stuff in there available soon, and so you can go out there and save some degrees of freedom. Thank you very much.
One question, remark, comment in the audience and also in the web.
Can you comment on Maxwell?
Well, we absolutely want to, go on and prove this for Maxwell, but somehow even obtaining, I said even obtaining results for a uniform mesh, right? And again, these sort of the results. I mean, this bound, this sort of master bound for the uniform mesh, no one has proven this yet for Maxwell. So I mean, this is something that I'm working on, but yeah. So a uniform mesh first, then of course do this for non-uniform meshes, do this for BEM. These are, again, this is the wish list for Santa since it's around Christmas time.
And the technical issue relates to lack of compact on basic.
Yeah. So for Maxwell, as always, it's this null space of the curl that is sort of annoying.
So you have tools to compute the tracking zone. If you give you a domain with an object, and it's easy on your graphic, but in true life.
So that's a good. I mean, that's a great question. That again, the question of given some obstacle, you need to do ray tracing to find out where the track rays are. This is going to be difficult or not straightforward. We haven't looked into it. We have plans to look into it, but this is sort of reflecting the fact that I mean the rays dictate the behavior of the solution. If the behavior of the rays is difficult to find, this is sort of a reflection of the inherent difficulty of this problem.
Just one question. When you look at these estimates,
yes.
Here in the given region, on the left-hand side, on the right-hand side, you have dependence everywhere.
Yes.
Okay, but it's not shown on your last slide.
So
yeah, this one, yes.
So this is an error. I apologize. This is an error. This should be. Sorry. This should be.
Okay.
Everywhere. No. Yes. So that's one perhaps disadvantage. Well, disadvantage is that ideally you would like to know how the error. How the error is sort of to term by term, but we don't.
So if Kadosk, you can speak.
Yes, hi Euan. Is your result? Can you use your result to do some a posteriori error estimates, comparing the region where it goes faster to the region where it doesn't?
Yeah. So this is again on our wish list, on our to-do list, but we haven't seriously tackled that. But yes, but it's natural to then think about using this notion of the different regions and the fact that the error is behaving differently in each region in a posterior error estimates.
And also Eric Savin have a question on the web. And the question, are there similar results for boundary integral equation?
So again, so this is again on our Stanton's wish list, but so there it's more so there it's a bit more complicated. So I'm just so here we had this nice result about how the solution operator depended, on where your source and location positions were. In the boundary integral world, there are results where you can write the inverses of your boundary integral operators in terms of solution operators to the PDEs, but there's that additional level, right? Like here we've got the PDE solution result. Now we need to go and input that into the integral equation theory to see how the integral operators depend on sort of where your source and measurement locations are on the boundary. Hi.
In the past, I used to for boundary integral equation. I need asymptotic expression when k tends to 0 and k the Green's function. Boundary integral is different.
Yes.
You have the variation with k, function of k is the Green's function. So you can use asymptotic expression and truncate your domain in k, but not tense. Here your mesh need to follow the k. But it's not the case in the boundary integral equation.
So for BEM, so whereas even in the non-trapping case, I have some pollution effect in FEM.
Yeah.
So yeah, for some that integral equation problems, you don't have the effect, so you can just take a fixed points per wavelength.
Yes.
I'm not sure.
No, what I mean is you can do the mathematical expression when k tends to 0 and infinity.
Yes.
And not directly in the boundary integral equation.
Okay, so you're saying somehow use some asymptotics of the final solution in your integral equations.
You just do the finite element computation on the truncated domain of k.
Okay, so yeah, so that's not so.
I use in periodic problem.
Okay, so maybe afterwards you can tell me about.
We confuse the synthetic expression, and because we have it's not exactly done, because we have a special kind of program.
Okay.
Involving 1/square root and Chebyshev function.
Okay.
So we derive a synthetic expression and can because you have the Green function in that case. The behavior in infinity and 0 is 1/k behavior.
Okay.
Proportional. And can be treated mathematically.
Okay, this sounds interesting. Yeah.
Okay. So I think no more questions. So thanks.